So we come across this question: what if the pressure of a gas in a container increases? So let's have a look at a container of a gas. Okay, let's say we have this container. Okay, and then there is a bubble molecule of gas inside here. Okay, which is actually colliding to each other and colliding with the container wall. And suddenly you have a piston, and in order for the pressure increases is by actually pushing this piston downwards. Okay, and then you are making the molecular gas become tight to each other. It become compressed to each other. Okay, so that will be what will happen if the pressure of the gas. So what happened to that particular gas? The gas is actually becoming too tight, that is trying to push each other away. Okay, it becomes so tight among each other, but the container itself is actually having a lot of pressure. Okay, because for example, like there are also pressure from outside, so it makes that the gas move a little bit slowly, okay, compared to what they could do if let's say there is no pressure for them. Okay, so similarly, if let's say you have a volume, okay, another container, but if let's say the volume is reduced, okay, the volume is reduced, again it is a similar case like the pressure. Okay, because the gas is no longer, even if let's say you contain the same amount of the gas, but it's actually it become tighter and it become close to each other. What if the heating temperature for a sealed container containing gas increases? So for example, if let's say there is some heating provided, okay, so what will happen? So the volume of the gas will expand. So this piston will push upwards, and the molecules are much more freely to travel and hitting the container of the wall. Okay, so they become more active. What if a greater number of moles of gas in the container? Okay, so if let's say you are putting instead of they have some gases, you add up more, so what will happen again within the same volume, they will become tightened. Okay, if let's say like you are imagining you are putting people inside inside the system, okay, in a lift together, so what will happen, they will become cramped, so not enough movement, right? So and then people got COVID. Okay, just joking. All right, so that is actually some of the things that we're going to look into. What will happen to the gas mixtures if let's say this situation happen? Okay, for solid and liquid mixtures is easy, but what happened to the gas mixtures? So we supposed to look at the physical properties of gases. Okay, physical properties of gases is saying that we are actually consider the behavior of hypothetical imaginary gas in which no molecular forces exist lead to the definition of an ideal gas. What does it mean by ideal gas? Is that if let's say you have a container, okay, and then you have a molecular gas, okay, okay, and then you have another closed. What happened is that the ideal gas assume this particular molecular gas, they doesn't collide to each other. What they did is just they collide to the respective wall. Okay, they don't collide with each other, but they just collide with the wall of the container. So only then it reflect what is actually the ideal gas. So the behavior of such gases can be characterized by an expression that relates volumes to temperature and pressure, which means that we call them as equation of state. So this is where actually we have PV equals to nRT. Okay, PV is equals to nRT. And then the EOS relate the molar density or specific molar volume of a fluid to the temperature and pressure of the fluid. Okay, so here you can see that it is relatable to what we call as pressure, temperature, and then we have an ideal gas. Okay, so you have this particular expression to really explain about ideal gas. Okay, so ideal gas, it can be derived from the kinetic theory of gases by assuming that the gas have a negligible volume, okay, and it exert no forces on one another. As I mentioned earlier, when you have a container, the molecule, it doesn't exert forces to each other, but it's actually collide with the container wall. That's all. Okay, and in such a way that only then we assume PV equals to nRT. But the gas itself said that I'm mischievous. What does it mean? I'm mischievous. Means that they are not simply obeying the law itself, but for the sake of relating it to the gas, to an ideal gas equation. So we have this particular equation as PV equals to nRT. And R itself is the gas constant. So here you have many ways to express about the gas constant. So you have many units to express the gas constant. This is where actually that you have learned in the first topic about the dimension, okay, unit and dimension. And the ideal gas equation of state is also state that PV is equals to RT, okay, where V prime is equals to V over N, which is actually, it means this is a specific molar volume of the gas, okay. And a gas whose PVT, okay, is supposed to be, there is a prime here, PV equals to RT, where this one is V prime, okay, is equals to V over N, or the flow rate of the volumetric flow rate divided by the mole flow rate, okay. A gas whose PVT behavior is well represented by the ideal gas equation is to behave as ideal or perfect gas. So I would like you to actually watch this YouTube video, try to click on this, and you'll be able to learn more about gas equation of state.